Okay, looks like we're good. Okay, so today we're going to be talking a little bit more about polynomial functions. We're going to talk about rational functions, which will be a new topic, and we'll see how far we get with that. And then maybe we'll get into exponential functions. It just depends. And then we'll have class again on Wednesday. And Wednesday will be our last class with new material. And then next Monday, we'll have a review for the final. And then next Wednesday, we will have the final exam. So are there any questions over what the plan is on how we're going to cover things the next 2 days? How about these homework problems? I sent these out via email. Would y'all like me to cover these and go through and show you the graphs of these 4 functions? Or do you feel like... Go ahead, Anthony.
Yeah, can you like go over like at least 1 or 2 of them?
Okay. Do you have a request?
Not necessarily.
Okay.
Maybe.
Let me do, I guess, the second one, because it's a little more involved than the first one. So let's start with number 2. All right, so for number 2, we're asked to sketch this polynomial function. And we went through a set of steps on how to do that. And then we had some technical problems and I couldn't continue class. But the steps we had, where were they? There we go. So we're going to make sure we're looking at a polynomial function. We're going to use a leading coefficient test to determine what's happening on the ends. We're going to find the x-intercepts. We're going to figure out what their multiplicities are, which will tell us if we bounce across there. And then we'll plot all the information and just connect the dots. So for this number 2, the first step is it a polynomial function? And yes, it is. The second step is to determine the left and right-hand behavior by using the leading coefficient test. Now, this function is factored, which means that we have to think a little bit about what the degree and the leading coefficient of this function would be. So what I told you to do was to look at each of the factors. So like this x squared, well, x squared acts like x squared because it's just x by itself squared. But the next factor, x plus 3, we ignore the 3 and we just say, okay, that's really acting like an x. So it's almost like we're multiplying an x squared times an x. And then this next one, x minus 8, we have that to the 3rd power, which means it's really acting like an x cubed. And then this last one here, x minus 2, we ignore the 2, so it's really acting more like an x. So this just gives you like this is a shortcut to figure out what the degree of the polynomial is going to be. So if we were to multiply all these together, we would add the exponents. So we do 2 plus 1, that's 3. Add another 3, that's 6. Add another 1, that's 7. So this is really like x to the 7th. And we'd also have a 1 in front because all of these have 1s in front of them. So for step 2, the degree of the polynomial is 7, which is an odd number. And then the leading coefficient is 1, and that's a positive number. And if we go to that table that I gave you last class, if we look at the table, this would tell us, the table would tell us that the left side goes down, in the middle we don't know, but then the right-hand side goes up. So any questions on that first, or actually the second step? We're okay? All right, the third step then is to find the x-intercepts and their multiplicities. So this comes by taking each of the factors and figuring out where there's 0. So if I look at the first factor here in yellow, x squared, and I ask myself, when is that 0? Well, that's only 0 when x is 0. Is my audio okay?
Yes.
Yeah.
Yes, okay. Then we look at the next factor, which is x plus 3. We set that equal to 0. Now, I'm not going to show that step, but what I'm doing is x plus 3, I'm setting it equal to 0. subtracting 3 from both sides. So x is negative 3. That's our next intercept. And same with the x minus 8, and solve x, we get x equals 8. And the last factor, we get x is equal to 2. So that's just setting each of those factors to 0. Now we need to figure out if we bounce or cross. And to do that, we go back and we look at the power on the factor. And if we look at this x equals 0, that came from x squared. And notice that 2 up there, the power. Anytime the power is even, what do we do?
I think you jinxed yourself because as soon as you said that, your audio started messing up again.
Really? Okay.
Yeah.
I'm going to stop my video. Sometimes that helps. Okay. Is that any better? We'll see if that gets any better. So notice we have a power of 2 on the x. Y'all copy that or no?
No, your audio went out again.
What the heck is going on? Oh, this is ridiculous. Okay, so my audio is still bad. It's cutting out.
Yeah, it was earlier. I mean, right now it's good.
I'm not sure what the deal is. I mean, I've got a good connection. It's weird. Okay, so do we bounce or cross at 0? Because we have a power of 2 there.
You bounce.
Bounce. Okay, so we're going to bounce here. Okay, and if we look at x equals -3, the power on that factor was whatever power's up there in green, and since it's not there, it's really a 1. And what we're looking for is odd or even here. So 1 is an odd number, so we should cross here. And then we look at x is 8. That comes from this third factor. There's a cubed up there, right? Third power, that's odd. So we will cross. And then we look at the last one, x is 2. And we look at the power up there. There's no power there, so we just say it's 1. That's, again, odd. So we should cross. And that's it. We're ready to put everything together and draw a picture. So I draw my x and y axes. And I'm going to put all these numbers here. So x is 0. X is -3. X is 8. It's way out here. And x is 2. Make sure they're. And we also know that the left side goes down, so I know this side goes down. I know the right side goes up. I'm just connecting all these things together. Move to the right. And go to -3 cross through. So I'm going to go here. I'm going to cross through -3. But when I get to 0, when I turn back to go to 0, I'm going to have to bounce. So I bounce off. And turn back around and go through 2 across. And I get back to 8, and I'm going to cross through at 8 and connect it. There it is. So that is what we're looking for right there. Everyone's look a little different, but we should all have the same behavior. We all have the same. Oh my gosh. I don't know what to do, y'all. I don't know what to do.
It's weird. It's like when you're explaining, it messes up, but when we're talking about the audio, it's fine.
Yeah. Maybe it's because I'm writing. Let me think about something here. Let me see if this is any better. Okay. Testing, testing.
Good right now.
Okay, so I'm using the microphone off of my webcam instead of this other one. So let's see if that holds up any better. Y'all just let me know if I start cutting out again. Okay, so this number 4. So what is the big difference between number 2 and number 4?
Number 2 factored.
Yeah, number 2 is factored. Number 4 is not. And I told you last time, there's pros and cons. When it's factored, the easy part is the x-intercepts because you can just set each of the factors equal to 0 and you're done. The harder part is figuring out the degree and the leading coefficient, part 2. Whenever it's not factored, like number 4, the easy part is the end behavior, the leading coefficient and the degree. The hard part is the x-intercepts because you have to actually factor it. So let's just start off here. First step, we're going to it is a polynomial function. Second step, okay, the degree is the highest power of x that we see. So it should just be 5, and that's odd. And then the leading coefficient is 1 again, which is positive. So this one's going to do exactly what number 2 did. The left side goes down, the right side goes up. Now the x-intercepts, the harder part, is we have to factor this. So we have to sit here and take this thing and try and set it equal to 0. Okay, and then we just go through the steps for factoring. So the first step for factoring is GCF, and hopefully you notice that all of these have an x squared in them, right? That's the most number of x's that appear in all of them is x squared. So we can factor an x squared out. We'd be left with x cubed minus 7x squared minus 4x plus 28. And then we look inside that parentheses and we say, can we factor that? And so we count the terms and we see that we have 4 terms. So when we have 4 terms, we do grouping, which means we'll just put a little slash there after the second term. And then I recommend that you just rewrite everything, x squared, big parenthesis here, equals 0. And then go ahead and let's do the grouping on that inside piece. So for the first 2 terms, we can pull an x squared out, which leaves us with an x minus 7. And then on the second 2 terms, I'll do that in different color, we're trying to pull something out, but we need to be left with an x minus 7. So I told you in the past that you could just put x minus 7 there and then try and figure out like what would go there. Can anyone tell me what number would need to be there to give us back negative 4x plus 28?
4.
Yep, 4. Okay, so 4 almost does it. That would give us a positive 4x minus 28. We want a negative 4x plus 28. So not 4, but what?
Negative 4?
Negative 4. Yep, so we put minus 4 there. That's an important step right there. That getting that negative is important because the next step, as you'll see, is to write x squared. Then, let's see, because these 2 match, we just write that down. And then in another set of parentheses, we write the 2 things that were out front. X squared minus 4 equals 0. Now, the reason why that minus 4 was so important was because x squared minus 4, this part here, is a difference of squares. So that's, again, another thing in factoring that we should recognize. So it should turn into x plus 2 times x minus 2. And now we've factored everything. Any questions there? My audio's better now?
Yeah.
Okay, good. I don't know what the deal is. That's weird. Copy. So. Okay, so now at this point, we set each of those factors equal to 0. So when we set that to 0, we get x is 0. When we set this one equal to 0, we get x is 7. When we set the next one equal to 0, we get x is negative 2. And the next one equal to 0, we get x is 2. So I'm skipping the step of actually solving those. Now, what happens for each one of these? Which of these do we bounce off of? Can you tell me which one? Anyone?
0.
0.
0 is the only one we bounce off, and that's because it has a power of 2. All the others have no power written, which means that they're 1s. So I should be crossing through on all those. So I'm just going to put C, C, C for cross. And now I'm ready to draw it. Okay, so I'm going to put them down here. 0, 7, negative 2, and 2. Left side goes down, right side goes up. This is a lot like number 2. Really, really a lot like number 2. We're going to cross through at negative 2. We're going to bounce off at 0. We're going to cross through at 2. We're going to cross through at 7. Yeah, that looks a lot like number 2. But these two problems, I hope that you can recognize the difference between, you know, how you go about doing them. I think that this problem number 4 is harder because it involves the factoring step. Okay, any questions before we move on to rational functions?
So a question on the test, are you going to have the chart for the direction where the...
Yeah, I'll give you that.
Okay.
I'll give you, so Anthony's asking, am I going to give you that chart that shows, let me see if I can bring it up here. One more page. There it is, this one right here. This chart, I will give that to you. Now, you'll have to know how to use it, but I will provide you that chart. Okay, so last time, let me also say something. In the packet, you know, you have this packet. It has forms of this. I gave you, and remember at the end of class last time I gave you some problems. That's what you're going to see on the test. You're going to just see, I give you a... So the homework related to this is not really the same thing. So I don't want you to do that because you're never going to see that on anything. Now, polynomial functions, I explained a little bit last time that they're good at doing things that just kind of go up and down, like stock market, or if you're looking at, you know, sales of a company, they go up and down. You know, the whole idea behind functions is that we take something in the real world and we try and find a function that models it, and that, when you graph it, it looks like what's happening in the real world. So we're about to start talking about what are called rational functions. This is a different category of functions, and they're really, really good at modeling a certain type of thing. I'm going to show that to you. So I'm going to start this off with a trivia question. So I'm going to, this is a quote from a movie. I'm wondering if anyone can tell me what movie it is from, and I may mess this up a little bit. don't know what Ed Norton Jr. and Brad Pitt are in the movie
Fight Club.
Fight Club. Okay, so if you've never seen the movie, don't worry about it. So let's just look at this quote. The survival rate for everything drops to 0. What that basically means, that quote means, is that, you know, like, as time goes on, the chance that a person is alive, that drops away. Like, the probability that he lives a certain, you know, amount of time drops to 0. So let's contemplate this for a second. And this is like a theoretical thing, okay? So let's say that we have a graph, and this is time, and this is just the probability. And put probability that a person is alive, okay? So let's say, okay, so they are born and they are alive, okay? So we're gonna start the clock. And we're not going to get into a debate here about when that clock starts, because let's say we all agree that at some point the clock starts. So we'll say that's time 0. And we will put here the number 1, which means if you have number 1 as a percentage, 1 converted to a percentage is 100%, because you move the decimal point 2 places right. So 1 is 100%. Okay. Let's say a person is alive, we start the clock, so the probability that they're alive is 100%. Now, what's the probability to live through that first day? I mean, in general, right? Pretty good, right? Maybe the probability is going to drop a little bit, but I don't know. Let's put a time out here. How about 10, and then we're going to measure this in years. So what's the probability, just in general, on, you know, that a healthy person born is going to make it to 10 years old? Pretty good, right? Wouldn't you say? Pretty good probability. All right. How about, are they going to make it to, let's say, 50 years old? So the probability that you're going to live to 50 is pretty good, right? And at least in the United States of America, you know, you live a lot longer now than you used to. So the medicine, everything has come along. So I would say you've got probably, you know, more than a 50-50 shot of living to past 50. Would you all agree? All right, let's put another number on here. How about 100? So what do you think the probability is that you're going to live to be 100? Well, that's starting to drop down, isn't it? So this graph should start to taper off like this and start to drop away. Now, this is the part that's interesting. What is the probability that you'll live to be 100, 110? What do y'all think? Smaller probability, right, than 100?
Yeah.
Okay, so this is getting smaller. Now, what's the probability that you'll live to be 150? Let's put 150 out here. Does anybody here think they'll live to be 150? Does anyone want to live to be 150? What do you think the probability is that you'd live to be 150?
I mean, I want to say 0, but.
So you wouldn't say 0?
No.
No, okay. A lot of people would. A lot of people will say, no, 0. There's no chance you live to be 150. But, I mean, there is a chance. Just because nobody has ever lived that long doesn't mean it can't happen, right? As medicine moves along, who knows? Maybe someone will live that long. So we're talking about probabilities here. So we're talking about, is there a chance? So there is a chance, but that probability is going to be really, really small. Would you all agree? See how my graph is getting really close to being 0, but it's not 0. So what if I put on this timeline 300? Now I'm running out of space, but what if I put 300? What's the probability of a person living to be 300? Can you say 0 then?
I mean, no.
Yeah, I mean, this is the same argument. Like the chance that you're going to live to be 350 it's essentially 0, but it's not 0. I mean, it's such a small probability, but it's still something. It's still some number that's bigger than 0. So this graph gets closer and closer and closer to 0. So we would have to like zoom in. We would have to zoom into that to see that we're not touching. We're actually not touching there. It's really, I'm talking about right in there. We're really, really small. How about the probability of living to be 1,000? Same thing, right? I mean, just a small probability. Really, really small. So look at this graph. Does this graph look like a line? Well, no, right? Because a line should do this. And it would actually cross through. It would be 0 somewhere, right? It's still, right? It doesn't look like a parabola. Does it look like a polynomial? Definitely not. Yellow here. Yellow here.
You're cutting off.
So I'm cutting off. I can't do it. I don't know what to do. It's a different microphone.
So what I was doing right now is clicking the space bar every time it was about to cut off, but I stepped away to go check out my dog, and I started hearing it in the background, like cutting off.
I'm getting a thing on my Zoom that says my audio is having issues, but I don't know.
Is it your Wi-Fi connection?
Take that as a yes.
Yeah, she's frozen.
Okay, can you all hear me now? Okay, see, this is the same thing that happened last time. And this is crazy because I've tested this since last class and I thought everything was great. I think it's when I have everything going and a lot of people in here that when I start to have issues. Okay, so hopefully y'all got the I guess the gist of this. This graph that I have up here is not a line, it's not a parabola, and it's not a polynomial. It's something else. And we need something that does what this quote in this movie is doing. Say, on a long enough timeline, the survival rate for everything drops to 0. So we need some graph that gets closer and closer to something like 0, like the x-axis, without actually ever getting there. And so far, a line and a parabola and a polynomial, all three of those won't do that. But rational functions will. Okay, so what is a rational function then? Well, a rational function, the definition of a rational function is just a function that has a polynomial. Now, polynomials we just studied, right? We just talked about polynomials. But if you take a polynomial and divide it by another polynomial, you have a rational function. That's what a rational function is. So I'm going to show you some examples. Oops. Show you some examples of rational functions. Okay, all of these are rational functions. Let me zoom this in a little bit. So look at this first one. 6x plus 36, that is a polynomial.
Can you share your screen?
Pardon me? Oh,
Can you
am I
share
not
your screen?
screen? I got kicked out and came back. So I didn't realize it took off my share screen. So look at those, look at these functions here. We have a polynomial divided by a polynomial. Now, I highlighted 6x plus 36. Can somebody tell me the degree of that polynomial on top? What's the degree of the polynomial on top right now? It's the highest power of x.
1.
1. Okay, so we have a degree 1 polynomial on top. And on the bottom in green, we have a degree 1 polynomial on the bottom. Would you all agree? So that is a polynomial divided by another polynomial. That is called a rational function. Look at number 2. Polynomial on top. What's the degree of that polynomial on top?
2.
2. And then the polynomial on the bottom? 2 also, right? Now, they don't always have to be the same, okay? So let's see, look at number 5. Number 5 is different. Number 5, the degree of the polynomial on top is 1, and the degree of the polynomial on the bottom is 2. So you could have the same degrees, but they could be different also, okay? All of these things just look really, really weird when you graph them. So I think what I'd like to do is I'd like to graph one of these for you. I'll show you in a second once I bring this up. Just to give you an idea of what these things look like. Okay, so let's take a look at this first one. 6x plus 36 divided by 3x minus 10. There it is. Look at that function. That's definitely not a line. It's definitely not a parabola, and it's definitely not a polynomial. But do you see, it's real important for you to see this. Do you see that this function is doing this thing where it's flattening out? Do y'all see that? As you go out to the right, it's just kind of flattening. It's approaching something, but it's never actually getting there. And I can tell you what it is, but I'm not going to. I'm not going to give it away yet. There we go. Yeah, that'll work. There it is. So it's hard to see this, but this red function right here is getting closer and closer and closer to this blue line. Hopefully y'all can see that. It's getting there. It's never going to touch it though. If I keep going to the right forever and ever, it's getting closer and closer, just like that thing I showed you a second ago was doing. So let's see where that blue line is. Can y'all tell that that blue line is the line y equals 2? Can y'all see that that blue line goes through 2 and it's horizontal? So that is something interesting is happening at y equals 2. You can see it on the other end, it's doing the same thing. It's getting closer, but it's never touching. Now, there's another thing that's happening in this function that is somewhat interesting, and that I'm going to have to draw a different line. Let me see. X equals. See that green line? that green line is a vertical line, and there's something interesting happening there also. Can y'all see that the red function, I like to think of it like a wall. There's this green line that's like a wall in our graph, and as our red function comes into it, it's like it sees the wall and it's like, shit, I can't go through the wall. So it just like, it like turns up, okay? And then on the other side over here on the left side, it's got that green wall and it just kind of like turns down and goes down forever. So these two characteristics of rational functions are kind of what make them rational functions. These vertical walls and then these horizontal things that your graph kind of gets closer to. And we have names for these, all right? That's why I'm showing them to you. So let me close this out. Let me go back here. So when you talk about rational functions, they all look different, but they all have certain characteristics. So let's say we have a rational function that does this. Let's say we have a green line here. I'm going to make it dotted that our graph gets closer and closer to. And you know what? I need to fix this. And let's say we have this black line that acts like a wall. Okay, those are the two kind of things I told you are characteristics of rational functions. We have names for these. The name of this horizontal line is the horizontal. Now here's the weird word. I'll write it first, and then I'll tell you how to say it. Horizontal asymptote. The P is silent. Asymptote. It's a weird word. Horizontal asymptote. And I want you to always think of this horizontal asymptote as like, I like to think of it as like a magnet. And it pulls the graph towards it. Pulls graph towards it, or toward it, at the ends. So it's kind of like with polynomial functions, we had the left and right hand behavior and we looked at a table to figure that out. With rational functions, we have these things called horizontal asymptotes, which are like magnets that pull our functions towards them, but that's only happening at the end of the function, okay? So it's very important to understand that horizontal asymptotes really only tell you about what's happening at the end of the function. It tells you nothing about what's happening in the middle. Now, does anyone have a guess as to what we call this vertical line that's like a wall? Vertical asymptote. Okay, so we have a vertical asymptote. Now, a vertical asymptote is like a barrier, okay? You can't cross a vertical asymptote. You're not allowed to. It's a barrier. Can't cross it. And it forces the function up or down. Okay, y'all got that? Y'all with me? All right, so let's figure out now how we're going to graph these. And I think what I'd like to do is show you one more example. And maybe if I show you this example, we can start to figure out where these things come from, all right? Like where the vertical and horizontal asymptotes come from. So I'm going to do this on that graphing software. I'm going to do, how about x plus 4 on top and x minus 4 on the bottom. Those are polynomials, degree 1, right? The top one has a degree of 1, the bottom has a degree of 1. So let me go to my little my little software here and see if I can't graph that for us. So we're going to do x plus 4 over x minus 4. All right. All right. So now, let me ask y'all a question. What would happen if I tried to plug the number 4 into this function? What would happen? If I tell you plug 4 in there, what would you get on top?
8.
8. Okay, what would you get on the bottom?
0, 0.
0, right? And you can't divide by 0, can you? Division by 0 is not allowed. You can have a 0 on top, you just can't have a 0 on the bottom. So would y'all agree that you cannot plug 4 into this function? You cannot let x be 4. And do you see on your graph what's happening at x is 4? Look at this. Here's our x-axis. So here's 2, here's 4, and now look up and down from 4. Do you see that that's where we have that vertical barrier? Do y'all see that? That vertical barrier is happening exactly when x is 4. So if I, let me see if I can do this quickly. See if this will let me. Oh, that's big. Okay, so here's the graph. It said at x is equal to 4, you can see, not a very straight line, but you can see that that's where we have our vertical asymptote. And that's also, if you look at the function, that was what made the denominator 0. That's not a coincidence. That is how we will determine where the vertical asymptotes occur. I'm going to summarize this. I'll write it down and we'll be clear on it. But I'm just trying to show you that that's where something interesting is happening at 4. And we could tell by just looking at that denominator and asking ourselves, when is that 0? Then we know that that vertical dotted line should be on our graph at 4. Now there's something else interesting happening. What number would I plug into this function to make the top 0? I know if I plug in 4, positive 4, I'm going to get the bottom to be 0. But what would I have to plug into the function to get a 0 on top?
-4.
Negative 4, yeah. That would give us 0 on top, and it would give us a -8 on the bottom. So 0 over -8 is just 0. So look at your graph. Do you all see that when x is -4, that's right there? What is that? What is that? What if we always called that part of the function that crosses the x-axis? What do we call that thing?
The x-intercept.
X-intercept, right? So let me try and summarize what's happening here, because rational functions are probably the most difficult functions that college algebra students ever see, okay? Especially in the 1414 classes, we usually spend like 3 weeks on these functions. So let me try and just kind of summarize before we get too far. A rational function is a polynomial divided by a polynomial. If you look at the polynomial, if you look at the bottom and figure out when it's 0, that's where you're going to have these vertical barriers. If you look at the top, the numerator, and figure out when it's 0, that's where your x-intercepts are going to be. The only thing we still have left to figure out is where's the horizontal asymptotes going to be? Where's the horizontal line going to be? And that is harder to explain. It's not as simple as what I've just shown you. So I think it's time for me at this point to give you some steps, all right? And then we're going to work through an example. Okay, so steps to sketch a rational function. All right, the first step is, make sure it's a rational function. Okay, so we're just looking for a polynomial divided by a polynomial. The second step is to find the x-intercepts. And to do this, all you do is set the numerator. Remember, the numerator is the top, okay? Set the numerator equal to 0 and solve. Remember, these are going to be points on the x-axis, all right? So when we figure out where the x-intercepts are, we remember those are just points on our x-axis. The third step is to find the horizontal asymptotes. And how did I say we'd do that? Sorry, I meant to put vertical there. I apologize. I haven't told you how to find those. So how do we find where we get those vertical barriers? Set what to 0? Am I coming through, or y'all? Anyone want to take a guess?
So you set like each to a function or to.
So if we go back and we look at this one, where is it right? This one right here. That's the numerator, the top. Whatever made the top 0 is where we should have x-intercepts. Whatever makes the bottom 0. So if we're looking at this, what we want to do is the denominator, the bottom.
Cutting off.
I'm off. My audio is off.
You were cutting off.
Shit, y'all. I mean, I don't know what to do. I'm so frustrated. I'm wondering if there's
You did it again.
yeah.
It won't let you like troubleshoot your Wi-Fi connection to Zoom.
Maybe. I don't know if I can do it while I'm in a session. Anytime I've tried to go to settings during this, it locks me up. It's not hardwired. You know what I'm saying? I mean, that's pretty freaking fast right there. Well, that's not down. No, let's see what that is. Oh, my up's not that great. Can y'all see that?
Yeah.
Yeah.
What do y'all think? Do you think maybe it's my upload speed's too low?
I wouldn't think so.
Yeah, I mean, I don't know. It's really, really weird.
When was the last time you shut off your computer?
I think it did a restart. while ago, maybe a day or two ago. I might, you know what we might do? It's right 11:53. Why don't we do this? Let's close the session out. I'm going to restart my computer. Okay. And because I don't want to continue to do this and it keeps cutting out and it's bad for you. It's bad for me. Let me do a restart on everything. Let's come back at 12:15. I'm going to give you all a pretty good break here. Let's come back at 12:15 and we won't take a break after that. We'll just continue through. Does that sound good to everyone?
Yeah.
Okay, I'm going to restart everything. I'm going to make sure there's no updates for Zoom that I'm missing. And we'll come back and we'll do an example where we actually sketch a rational function. All right? So I'll see you, same meeting, same password, everything else. I'll see you at 12:15. All right.